Welcome back to Matrixology. Can actually talk again. Okay, so the plan is to go through some more work on determinants here, which are these strange beasts, and then get back into, that'll lead us back into the great, magnificent eigenvalue problem. But lots of fun with determinants first. So we've been through these two pieces of paper here, right? And the basic idea, just to refresh, is that we're going to think of a determinant as the volume that's created by the row vectors. So for instance, for a 2 by 2, we create a parallelogram out of it. Here are the two row vectors, and then we build them again. And if we have a 3 by 3, it becomes a three-dimensional parallelogram, and we call these things parallelepipeds, because that's ridiculous. Very fun. Parallelepipeds. Parallelepipeds. Okay, so we do that, and we went through these observations about what happens when we change matrices, how their parallelograms and ipeds change. And because there are areas and volumes and so on, we have good intuition for them, right? So if we double a row, for example, then we double the area of a parallelogram. And we got to this idea that we could rearrange the rows, do things to the rows, and get ourselves back to the identity matrix, which has a very simple, in the case it's a unit area here, right? So we can have a hypercube for an n by n. So we don't really need to know how to measure this thing at all. We just need to know how to reshape it. And we came up with 3 rules that the volume of the identity hypercube is 1. Fine. If we swap any 2 rows of A, then we just change the sign of the determinant. That's probably the most peculiar one. And determinants are multilinear in their rows. And this really follows from volume in a nice way. Okay, so if we multiply one row by a number, we have to divide by that number to keep the determinant the same. So if you want to multiply the third row by 10, you have to divide by 10 outside the resulting determinant by 10. Okay. And we can split rows. That's the multilinearity story. All right. So the plan is using these 3 rules to build up to some general results about determinants. And that's where we are now. So here they are again. So properties. Identity matrix. The determinant of the identity matrix is 1. This is for n by n's. I've pre-written these out. It took some time to just do it in the right way, and I didn't want to make a mess writing it out. So row swap, that's a multiply minus 1, sign change, so it's a sign flip, and multilinearity. And here's our so multilinearity, meaning it's row by row, right? Each row, it's linear in each individual row, which is an odd property. Okay, so this is notation. We'll generally use this. It can be a bit confusing because these are straight lines, and we see straight lines everywhere, and so they're not square. They're not square brackets. It's easier to kind of get that wrong. So let us therefore struggle ahead anyway. We have nevertheless, I should say, and you'll see this as well. People write the determinant of A. Fine. All right, so. Simple thing, if we multiplied, so we're going to have how many results? We're going to go through A, B, we're going to get up to J. Yes. Lots of good things. Right? So some will be easier than others. So the first one, if we take A, so here's our matrix, n by n, we multiply it by some number, then that means every row is being multiplied by that number. Right? So T times 3, 4, 2, 1, right, is 3t, 4t, 2t, and t. And when we go to determinants, linearity applies to each row, so we have to pull the t out of this one, and then out of this one at a time. So we have n rows, we have to pull out a t for each row, so we get t to the n. So this makes sense from a volume point of view again. So if you think of this as, say it's a 2 by 2, we have a parallelogram, we stretch both dimensions of the parallelogram by a factor of, say, 3, right? then that increases the area of the parallelogram by 3 squared. And in general, it increases it by a factor of t to the n. So, all right, so that's a simple first result. All right, so you need to know. So this is odd. It's not t times a, but when you think about volumes, it makes sense. It's not. Sorry, it's not. The easy thing to do would be to pull out t, right? T times the determinant of a, but must think of it as a volume. How do volumes behave? If two of a's rows are the same, then the determinant of a equals 0. So we do have a well. So let's think about it. So 2 rows are the same. So that means 2 of its vectors making its parallelepiped are the same. So that should be the plan there, the kind of giveaway there, right? So let's have an example: 3, 4, 3, 4. So these rows are exactly the same. We're allowed to swap rows. That's one of our ways of adjusting matrices and understanding how they behave, their determinants behave. We get a minus sign. That's property 2. And these have been swapped, right? So this one went to here, and this one went to here. Of course, it's the same. And the only number that is equal to minus itself is 0. So that must be true. Of course, if you know, we have a formula which we've derived separately for parallelograms, so 3 times 4 minus 3 times 4, fine. But we're not using that here. So here's a 3 by 3 example. 366, 366, so the third row is different, but we can again do this, right? So we swap, right? Row 2 and row 1 change, they swap. We introduce a minus sign, it's our rule, so again it has to be 0. And so if we go back to that first example, here's the parallelogram associated with it. Right, it's squished flat. In fact, it goes up to 6 and 8, because we stack them. So imagine these two vectors are the same, and these two vectors are the same, one big straight line. So it takes up 0 area. This is in 2 dimensions. It's a line, which is fine, but that takes up 0 area. In general, 0. This piece here essentially makes a parallelogram in 3 dimensions. So it's just a little thin piece of paper. It's a little thin piece of paper in 3 dimensions, which constitutes 0 volume. So that's what's going on. It's collapsed. Okay, so there's a basic result. 2 rows are the same, then determinant is 0. So if we do one step, so here's a great thing that we've done, right? So many things in the course have been built from the start, so that we're happy now. We don't have to say, oh, all the methods we used before are wrong. We're going to use standard row operations and show that does not change, right, the value of the determinant. So this is a standard row operation. So here's an example. Change in row I is the old row I minus the multiplier Lij times Rj. Alright, so it could be row 3 prime equals row 3 minus 7 times row 2. And this is indicating there's a 1 here. That's one of our things that we did. We didn't put the row I prime is 4 times row, row 2 prime is not 4 times row 2. It always had to be row 2 minus another row, a multiple of another row. This turns out to be really crucial, again, when it comes to determinants. Alright, so the monks have shown us the way, and we have been faithful. Alright, so here's a little 2 by 2. It's an abstract one, and let's get a glimpse of how this behaves well, right? So, again, our old row operation story. So we've got A1, this is just an abstract 2 by 2. We're trying to get rid of this, zero this out. Here's the lineup. Row 2 prime, second row, is equal to the old row 2 minus L21 times row 1. And as we know, this is A21 divided by A11. Right, this is a pivot up here, and that will be our multiplier. We'll just leave it as L21. And it looks like a extra 2. All right. So it's a tilde, and that means, that always meant to us that these are not the same matrices, but the solutions to the systems that they describe for AX equals B are the same. And that was the whole game early on when we got to LU decomposition, was we were moving from messy systems to simple systems, and all through that connection they all had the same solution. So that's why we say it's a tilde, it's not equal to it. We'll change that in a second. Let's see, so top row does not change. It's A1, 1, A1, 2. And then here's our row operation, right? So it's A21 minus L21 times the first entry up here. And then A22 minus the multiply times, see, we got a little carried away there with the 2's. Just got it wrong. Okay, yeah, A1, 2. Now let's look at what, so we're interested in general about determinants now, so we know what this, we'd like to see if this changes, what's the determinant of this thing compared to this one? Is there a simple relationship? And we're saying it's going to be the same. So let's see. So now we're going to find the determinant of this matrix. Right, so it's been modified. Again, the second row is really here minus some multiple of the first row. So I've just rewritten this whole matrix out here, and then used the property of multilinearity here to spread this apart. And we can break it in any way we want. And so a very natural thing to do is to leave the part of the original A matrix here. Let's call this A. The original A matrix here. And then we want minus L21. That's our multiplier. And A11 and A12 will end up on the bottom here, right? So multilinearity did a couple of things for us here. It split these two vectors apart, and if you like, this will be just a big plus and minus L21 A11 here, minus L21 A12 here. But then we can, this number is multiplying both of these quantities, right? It's multiplying the whole row. We can pull it out, again multilinearity, and then these rows are the same. All right, so we've got property B. This is property B. So this whole thing is zilch. All right. So we did one step of row operation, standard row operation. We take the determinant of what we end up with, and this goes away. We see we actually have the original matrix here, right? So we can keep doing this, and it won't change it. So that's kind of cool. If you want, right, to be more row operations, you can think about that as well. But you can keep doing this splitting and trim off the row operation part. Now, this is important. We went from a tilde here to equals. Right, so the determinant of this blob is equal to the original determinant, but these are not the same. These matrices are not the same. Right, determinant is one number. Okay, these are supposed to be item list indicators. So above generalized standard n by n, so we can do it by n, for n by n. And as I said here, right, the tilde for solving AX equals B means that they have the same solution, not the same system, becomes an equals when we're working with determinants. And here's the subtle notation difference of straight lines. Right, these are not matrices. This thing here is some number. Okay, so that unleashes all sorts of things, right? So if we can do standard row operations, then we can connect A to U, we can connect it to its reduced row echelon form. We'll get to that. So here's a first piece. If A's rows, so again it's an n by n, we're always talking about square matrices here with determinants, are linearly dependent. It's linearly dependent, right? So you can make one of these rows out of the others, if you like. Then the determinant of A, see, these things can go wrong. The determinant of A equals 0. Big deal. So we can use row operations, and ways to think of this. We can use row operations to make one or more rows of zeros, right? That's what's going to happen because they're linearly dependent. And now we could just add one of those non-zero rows that are left to the 0 row, and we'd have 2 rows that are exactly the same. And then we could use B again. Just this was sort of a funny, quirky result. We can use it here. So, and more generally, if you see a row of zeros, then the determinant is 0. Okay. All right. Now this, lots of other things. So here's another way to. Okay, let's put it like this. Let's give another reason for this. So here's an OR. So we can take that 0. So we've done our row reduction. We've got to some matrix, which is, well, we've got to some matrix with a row of zeros or more, one or more rows of zeros. We can multiply that 0 row by any number c. And multilinearity means we should scale the whole determinant by a factor of c. But the row's not changed, right? Because it was a 0 row. C times a 0 row is still 0. So the determinant has to be 0. So here's an example. Zeros along the bottom. This is the same as c times all of those guys, right? Multilinearity means we can pull this c out. And these determinants are the same, right? Nothing's changed here. So, and because we can choose any c, the only way for this to be true, that something equals any number times itself, then we have to have that it's 0. Okay? So other ways to think about that, but that's a sort of a start, right? So, and I'll say it again here. This is, if you look at this row, it's all zeros, which means that instead of before we had 2 rows being the same, now we have one of the axes of our parallelepiped, one of the lines, the core lines of it is 0. It doesn't have any size. So again, it's squished. It doesn't take up any volume in the n-dimensional space. So let's connect this to many things we know already. So the determinant of A being 0, again, this is only for square matrices, means that A's rows are linearly dependent, same as. The rank of A, right, which we've written as little r, this very important thing, is less than n. So the dimensions of the null space and the left null space, and this is because we have the same, here's our big picture version. It's Rn and Rn. Because M equals n, right? M equals n, it's a square matrix. They both have a dimension at least 1. So there's some stuff here. They're the same size, same dimension, and they're here. A has no inverse, right? And the big picture again, if you send a vector over to here, A times x, you're not sure where it came from, right? Because you could have added all these null vectors, or any null vector in here could have been added, so it's a many-to-one mapping. There's no way to know exactly where it came from. You can find the row vector, but not one unique vector. And so that means that if Ax equals B has a solution, because there might not be a solution, there's a left null space, then there are infinitely many, right? You can always add a null vector. And the geometric interpretation is if A's parallelepiped, defined by its row vectors, one or more of those sides has to have 0 length. Right. And yeah, right, it's true. We have one more other piece here, which is that one or more pivots are equal to 0. Good. Right, so lots of things here about when matrices go bad. They're not bad, but this is a class of matrices that have no inverses. All right. Very, very important. So let's do a little example calculation. So we've got this idea that row ops works. And here's our matrix. We're going to use this guy a few times. 1, 1, 1, 0, 3, 2, 2, 1, 2. All right, so we'll do this is useful because we can do a row swap straight away, or we see that we should have one, right? There's just a 0 there. We don't have to do that, but let's do it, right? And we're kind of stacking it up. So 0, so we've done that, so we've got a minus sign at the front. This is, you could call this freestyling, right? There wasn't a really principled reason for doing that. But we wanted to see it happen. All right, so we're going to do, so that's a swap. Row 2 prime is row 2 minus 2 divided by 1 times row 1. Normal row operation. Should feel very soothing. So the first row does not change. Third row does not change. The second row, so it's 2 minus 2. 1 minus 2 is minus 1. 2 minus 2 is 0. Now we've got to get rid of this character. So it's row 3 minus 3 divided by minus 1. Same method. We've still got a minus sign hanging around the front. 1, 1, 1. First row doesn't change. Second row doesn't change. 0 minus 1, 0. And then it's going to be 3 minus minus 1 times 3. Did I get that right? Yeah, all right. So essentially 3 plus 3 times minus 1. So we end up with 0 here, and then 2, and there's a 0, so it's 2 minus 3 times, fine. So it's 2 plus 3 times 0 is just 2. All right, the pivots have been unveiled. So we've got 1, minus 1, and 2. This is a version of the upper triangular matrix. You can do row swaps like this. It's okay. So the pivots aren't universal. So let's keep going. We can do 2 more row operations here, and I've sort of stacked them. So the first row, because of the simplicity of where we are, we know we can just use the second row to get rid of that number. It's all zeros. Third row to get rid of that number. We'll do them one after the other, so that's why this is double prime. But essentially you just clean this off and you clean this off and nothing else will change. So there's going to be 1, minus 1, and 2 are still there. All zeros, and our minus sign is still at the front. So now we use multilinearity. We're allowed to do this right at the end. We're going to pull out, well, D1 is just 1, D2 is minus 1, and D3 is 2. So we're going to pull them out, minus 1, 2. And we're left with the identity matrix. We know the volume of that is 1, and minus minus. So we've got a 2 times 1, and we end up with 2. So there's a standard that's a straightforward calculation. And in general, yeah, you follow the principled way that we do our row operations. All right, so a couple of things that appeared there. That we can immediately write down as results is that the determinant of A, right here, we got the U here, it's going to be the determinant of U plus or minus, with a plus or minus sign out the front. And that depends on the number of row swaps that have occurred in getting to U. Right? And the row swaps we've encoded in here. We've talked about them somewhat abstractly, I suppose, but we end up with this idea that you could do all the row swaps first. Right? So this is our permutation matrix. Not to be confused with projection. Unfortunately, we have a limited letter scope. Okay, so that's cool. All right, so that's a good thing. And what is it in fact? It's actually, you can see it here, right? There was really a 1 there as well, which was the first pivot. So it's plus or minus the product of the pivots, and we use D for pivots. So this all follows from the, so that's kind of a big deal. So the determinant of A is the product of its pivots. These funny things that have been important early on, they've cropped up again. And then there's a ambiguity here with plus or minus, so it depends on the number of row swaps. And so straight away you can see if one or more pivots is 0, then the determinant of A equals 0, and that's the result we included back here. Good, cool. So these are very nice things, right? Matrixology is full of beautiful little things. All right, okay. Next result. So this is a big one. Determinant of A times B. So they're both n by n matrices, is the determinant of A times the determinant of B. So volume of whatever parallelepiped this thing is equal to the volume of the first ones and the second multiplied by the second one. So that's a interesting thing to try and think about there. But there you go. Okay. So maybe a couple of things to note, right? So if one of them has a determinant 0, then the determinant of the whole thing will be 0. Think about that. But it allows lots of other calculations to come out. This is a good thing. A plus B, there's nothing there, right? That doesn't have anything. But A times B, beautiful. So, a number of different proofs. I'll give you this one. The monks told me to do this. So, we're going to use row reduction. And so this is going to be a little abstract looking. this piece, but here we go. So we perform our permutations on A, we collect them all in one big matrix, and then this is going to be all of our elimination matrices stuck together. All right, so they do all the row reduction, and that gets us to the reduced row echelon form of A. Which, well, you know what? Let's, it's true, it doesn't get us all that. Yes, so let me get this right. This should be what I'm going to call here an E, and I had this on some previous ones. It's the reduced row echelon form, and I gave it a name, I think. Yeah. We're almost there, you see, with the row reduction, but we've left the pivots in with pivots. Still in. Which is really the pivot matrix if you know, everything is good and we've got all the pivots are not equal to 0. Okay. Right. So let's imagine that that's the case, that all the pivots are not equal to 0. So when we do the row reduction, we get to a diagonal matrix, and all of the pivots are on the diagonal there. All right. So AB, determinant of AB, we can perform row reduction, and we know it's the same. So that's what it's here. Right, row reduction, determinant is unchanged with row operations. So the determinant of this is equal to, depends on the permutations, plus or minus inserting all of these row operations into here. Okay, good. And we've chosen the row operations for A because it's A times B. So we apply all of these and we just get the diagonal matrix with A's pivots here. So this is pretty simple, right? This thing looks like, well, here it is on the next line. It looks like so it's a diagonal matrix. It's got the pivots on the diagonal. Zeros everywhere else. I'm going to take B, which again is a square matrix. I'm going to write it as B1 star, so that's its first row, second row, nth row. So if we do this multiplication, it's D1, all these zeros. That says I want this row vector 0 of the rest. So D1 times B1 star. So D1 times the first row of B, D2 times the second row of B, Dn times the nth row of B, and they're all stacked. So now we've got this as a square matrix. Well, I guess that's fine, yeah. I was going to do 2 sets of brackets, it's silly. Alright, so there's all these numbers in our box, but our box has straight lines. We're trying to find the determinant. Multilinearity means that we can pull out each one of these pivots. D1, D2, we're going to pull them all out. We've got a plus or minus still. We've got our product of the pivots of A multiplying the determinant of B, because the thing that's left is B, right? If you pull this out, D1 out, you pull the D2 out, one at a time, multilinearity, then this is the determinant of A, multiply the determinant of B. So, that's pretty cool. And if we have one of A's pivots are equal to 0, then when we do row reduction, we'll get a 0 row, and that'll create a 0 row here when we make this product. Right, there'll be a 0 row at the bottom, say this pivot, and so therefore the determinant of that should be A times B has to be 0 as well. All right, let's keep going on. All right, so we assume there was no pivots were 0. Got to this nice result. Determinant of AB is determinant of A times determinant of B, and if in case of zeros, then we have a slightly different result, and we can say that the both sides are 0. All right, good. Okay, that's cool. Fine. Right, so that's a big result. So here's something that follows immediately, very nicely. Is the determinant of the inverse of A is 1 over the determinant of A. And so one way to do it is let's just multiply A and with its inverse. We'll just use exactly this rule we created. So it's blob times blob, blob blob, equals the determinant of the first blob times the determinant of the second blob. At the same time, of course, this is just the identity. A times a to the minus 1 is the identity. The determinant of the identity is 1 by our definition. So now we have the determinant of a times the determinant of a minus 1 is 1. So we can flip them around however you want. Determinant of a is 1 over its determinant of the inverse, etc. So if the determinant of a is 0, then the determinant of the inverse is infinity. So you can see that's not going to work out, right? So if you have a parallelogram that's all folded up, it's got 0, then the inverse for that matrix would have to have an infinite sized parallelogram to cope with it. And so these things just don't work. And so here's the sense that a matrix, which it's an n by n, it's full of numbers, it doesn't look like 0. Here's where its zeroness is. Right? It's in the fact that it's got linearly dependent row vectors and column vectors. That's where it's got a 0. You can sort of reduce it back to our normal sense of what non-invertibility is for basic numbers. Okay, so that's a nice little result. We've still got a couple more to do. And this one is somewhat quick. So it's the if we have an upper or lower triangular matrix, so it's all zeros below, so if it's upper, it's all zeros below the main diagonal. If it's a lower triangular matrix like L, in LU decomposition, it's all zeros above the diagonal. Okay, then the determinant is a product of the entries down the main diagonal. And so row reduction on a triangular matrix, there's no row swaps, you don't have to do any row swaps. You don't change any entries on the main diagonal. Right? You've got this main diagonal, you just use all of those entries, they're your pivots, to either get rid of everything below it, if it's a lower triangular one, or get rid of everything above it. And we know the determinant doesn't change, so you'll clean all of those off, you'll just end up with the main diagonal, and then it's the product of everything on the main diagonal. If one of the main diagonal, if you've got a triangular matrix and one of the main diagonal entries is 0, then you're going to end up with a row of zeros. And so the determinant will be 0 as well. So it's going to work out, right? It's still going to be true. So the product of if there's a 0 on that main diagonal, that's going to give you a 0 determinant. All right, so here's an example. So the nice thing about this is you don't have to calculate anything complicated. We're going to figure out how to calculate determinants in a little while for n by n's, but you see it's a bit of a mess, but 4 minus 3, 2, that's all. You just multiply those numbers together. It doesn't matter what these numbers are. You put anything in here, doesn't change it. Here's a lower triangular one, 4, 1, 2, that's it, 8. Doesn't matter what these are. And so what I was saying up here is, yeah, you can just sit here, you'd be able to use this 400 to get rid of the 77, 13, the 1 would then be able to get rid of the 99. So here's one that has a 0 on the main diagonal. Again, doesn't matter what these things are. It's tempting to think that's going to matter, but it's 4 times 0 times 2, 0. Right. So once again, we could get rid of things. We get rid of the 17 with the 2 and the 16. So there'd be zeros here. This is a pivot column. It's a free column, so that 77 has to stay. But we've made 0. We've made a row of zeros. So the whole thing has to have 0 determinant. Okay, so the last one, which then opens everything up that we've done before to be applied to columns as well, is that the determinant of A is the same as the determinant of its transpose. So you can, if you flip it, a matrix, then and calculate the determinant, you get the same thing. So it means that you can do column operations actually. You don't have to flip it and then start doing row operations. You can actually just flip it. If you see, for example, a column of zeros, then the determinant is 0. If you see 2 columns that are the same, then the determinant is 0 because of this connection here. So that's what we're saying here. We can use column ups in the same way as row ups, and all results for rows work for columns too. So that's great. Great. Well, lots of amazingly good things. All right. This is supposed to be a footnote. That's what, or a connection for later on. So, okay, so we're going to use this one of our first factorization, right? So some permutation of A can be written as a lower triangular matrix times an upper triangular matrix. And because we're working with n by n's, everything is an n by n here. N by n, n by n, n by n. Right, so in general, A and U are the same size. L is usually an m by m. All right, but that's not where. Okay, so we have this result, right? So we can take the determinant of both sides and split it. So we get the determinant of the permutation matrix is times the determinant of A is the determinant of L times the determinant of U. Right, so that's one result. We'll just put that off to the side. We can take a transpose of our factorization, no determinants yet. Take a transpose. We know the transpose rule, right? A goes to here, P goes to here, take their transposes. U goes to here, L goes to here, take their transposes. And then we'll take determinants of both sides, and again we have our rule for products. Very simple, right? So determinant of both of A transpose P transpose is determinant of A transpose times the determinant of the permutation matrix transpose. We have these characters, the determinant of U transpose times the determinant of L transpose. So these are diagonal, so they don't change, right? We know that they have the same from this result. The determinant is just the product of what's on the diagonal. These are triangular matrices. This is not right. That should be triangular. I know what I was trying to say. So these are triangular matrices. So we know that the determinant of U transpose is the same as the determinant of U. The determinant of L transpose is the same as the determinant of L. Awesome. So we're going to replace those, and we'll shift them into the order we had before. Right? So L and U, and I've just swapped these orders here. These are just numbers. Number times a number equals number times a number. So we have one thing left to handle, and if we can show that the determinant of this permutation matrix is the same as the determinant of its transpose, right? So if they match up, then everything fits, right? So the determinant of A transpose is sitting in the same equation as this one. Determinant of A. All right. So it's a permutation matrix. It's a shuffling of the identity matrix, right? So it's the identity matrix shuffled. So with some number of row swaps, you can turn the permutation matrix, any permutation matrix, into the identity matrix. So we know the determinant of P has to be plus or minus 1, right? So we're just, every row swap gives us a sign change. Eventually we end up with the identity matrix. Determinant of the identity matrix is 1. We also know, because it's an orthogonal matrix, we figured this out a while ago, that the inverse of P is its transpose. Right? So P transpose P. So it's the same as what we had for the same sort of business as we had here for the inverse in general. P transpose P, it's the identity. And the determinant, so we're taking determinants. Determinant of identity is 1. We can use the determinant of a product is the product of the determinants. So we've done that here. So the product of them is 1. We know that it's plus or minus 1. So we know that they're either both 1, right? 1 times 1 is 1, or they're both minus 1. So they have to match. So that's really the key thing. So they match. We're not sure if it's plus or minus 1. We can't know without knowing what A is, but we know they match up. So therefore we can replace this transpose, the determinant of the transpose of P, with the determinant of P. That's what happened there. It's either plus or minus 1, but it's the same. And then using this little footnote, which involves a Pac-Man. So this equation, bubble around it, looks the same as this one. The only difference is the A transpose, the determinant of A, and the determinant of A transpose. Therefore, they have to be the same. So that's pretty great. That, as I said, it unlocks all of these previous results, or any result you might have for rows, for columns, right? And so this does not work for row operations for solving AX equals B. It's just a special determinant property. All right, so that's that's a reasonable amount to cover here. And it gives you a way of calculating determinants. The next thing we have to cover is a different approach to computing determinants. It's somewhat magical, somewhat strange. It will give us a formula for solving ax equals b for x, for the inverse of a, again to solve for square matrices. The limit will be, why don't we use this all the time? Well, it has to be for n by n's, and it's actually still computationally expensive to compute determinants. There are a few other reasons, but we'll see some groovy things. It's what we do use when we're computing eigenvalues, especially for 2x2s and 3x3s and 4x4s. 2x2s we have a formula. We need a formula particularly for 3x3 and 4x4 determinants. And 3x3 determinants, very common things. We live in 3 dimensions. Okay. So I think that's a good place to stop, and I'll make the next one a separate video.